Yeah, we can do a couple of these. So here we've got some electron configurations, and they want us to identify the ion that has a 3+ charge. So if we see a 3+ charge, that simply means somehow there are 3 more protons than there are electrons in the balance of charges in this atom. And then they give us an electron configuration. So when we have an electron configuration, it's useful in a number of ways. One way we can look at an electron configuration is to figure out what level is the valence level. We can also look at that and recognize if we were to take some electrons out, where would they come out of? Or if we were to put more electrons in, where would they go? We can also look at an electron configuration and get a sense for the orbital diagram. So we know if we have 3 electrons in a 3D, we know that in a ground state they should be spread out with the same spin, so we could identify that atom as having some number of, in this case 3 unpaired electrons that are creating a magnetic field due to their spinning charge, and those magnetic fields not canceled out. And so if you have unpaired electrons spinning in the same direction, their magnetic fields add together. That creates a paramagnetic element, something with the magnetic properties. So we can say a lot from the electron configuration. Another thing we can just quickly determine from the electron configuration is the total number of electrons. So if you're given information about the charge, you know the relative quantity of the protons compared to the electrons. So however many electrons we have, we're going to have 3 protons more than that because we have a 3+ charge. And the electron configuration we can use to get the total number of electrons, because all we have to do is count them up. So if we have an argon core, argon has 18, so that should be 18 electrons plus the 3 electrons in the 3D, since it says 3D3, and that gives us 21 total electrons. So if we had 21 total electrons and a 3+ charge, how many protons should we have? 24. And the element that's defined by having 24 protons is chromium. So the answer to this one would be a Cr 3+. That's the symbol they're looking for there. So the element's defined by the number of protons, and the charge has to do with whether I've got extra electrons or whether I don't have enough electrons to balance out the charge of those 24 protons. So maybe we'll just do one more of those. So let's look at the last one there. Xenon 4F14 3D6. So that's D. So we could treat this the same way. It tells us in the beginning that we want there to be a 3+ charge overall. So we count up the electrons. So xenon has 54, it's element 54. So this would be the neutral core, right? If we're creating a charge, we're not changing the electrons in the core. We're taking out or adding valence electrons. So the xenon is the core. That's what the abbreviated electron configuration is telling you. It's telling you which noble gas core do you have, or how many electrons do you have in the core of this atom. So we've got xenon's 54 electrons in its core. Then we're adding 14 from the 4F plus 6 more in the 5D. So that's going to be 74 total electrons. Normally I would also have 74 protons, but that would be for a neutral element. And so that would be tungsten. However, I don't have equal numbers of protons and electrons. Again, I have a 3 positive charge, so I need to add 3. So if I had an element with a 3 positive charge and it had that electron configuration representing 74 electrons, it would have to have 74 protons to give it that 3+ charge. And so that is iridium. So that would be IR 3+.